Hello and welcome to a new video on IGCSE Classified Paper 2 Physics. In this video, we shall be discussing electromagnetic induction and AC generators. We shall begin with some questions on electromagnets. A strong electromagnet is used to attract pins. What happens when the current in the coil is halved? So, does it stop becoming a magnet? No, it doesn't, because the current is not removed, it's just reduced. So it's still an electromagnet. So what will happen to the pins? It will attract some pins, but not as many. This is a very logical question. Won't stop attracting pins, it will just attract a fewer number of pins because the magnetic field strength decreases. So B is the correct choice here. An electromagnet with a soft iron core is connected to a battery and an open switch. The soft iron core is just above some small soft iron nails. The switch is now left closed for a few seconds and then opened. What do the soft iron nails do as the switch is closed, and what do they do when the switch is opened? So of course, when the switch is closed, that means that you have a circuit, you have electricity moving through the circuit. So the electromagnet will work in a sense. It will magnetize the soft iron core and the nails will jump up, will attract the nails. So we're between A and B. Now, when we open the switch, there is no longer any current flowing in the circuit. And you should know that an electromagnet is easily magnetized, easily demagnetized. So as soon as there is no current flowing in the circuit, the electromagnet stops working. The soft iron core stops its magnetism. It is no longer magnetized, and it stops attracting the nails. So what happens to the nails? The nails fall down. So the correct choice here would be choice A. A bar magnet is placed inside a current-carrying coil. The diagram shows 4 different experiments. In which experiments is the magnet demagnetized? So to demagnetize a magnet, you need an alternating current, not a direct current. So this one is incorrect because it has a direct current. And this one is incorrect as well because it has a direct current. And you can either slowly remove the magnet or slowly decrease the current. They would both work, and 1 and 3 is the correct answer. So B is the correct choice in this question. Next, we move on to electromagnetic induction. Which statement about electromagnetic induction is correct? A strong magnet that is held stationary near a stationary conductor causes greater effect than a weak magnet. This is incorrect because you need to understand that electromagnetic induction requires a changing magnetic field. So what does that mean? There has to be some sort of change occurring. Either I move the magnet, or I move the wire, or I move them both in opposite direction, or I move them both with different speeds. But if they're both standing still, then there is no change occurring. If they're both moving in the same direction, in the same speed, again, there is no change occurring. So this actually helps us with choice B. Choice B is incorrect because, again, they're moved with the same speed and in the same direction. So the distance between them will always remain the same. So there is no change in the strength of the magnetic field. They're not getting closer together or further apart. So the magnetic field is constant. So if the magnetic field does not change, there is no electromagnetic induction. And of course, electromagnetic induction has to do with electricity being generated due to a changing magnetic field. So the idea is to generate electricity using magnetism. But for that to happen, you need the magnetic field strength to be continuously changing. Now, we're between C and D. C has to do with the magnet moving away. D has to do with the magnet moving towards the conductor. In fact, both of these are correct. So how do we choose between them? Well, the only difference between those 2 statements is this word here. This word is what makes D incorrect. because you can either move the magnet towards the conductor or away from the conductor. So C is correct, and D would have been also correct had they not said only occurs. The effect only occurs when the magnet is moved towards the conductor. This is incorrect. It could happen if the magnet is moved away from the conductor. So as I said, the difference between C and D is very slight. It's this idea of only. You're restricting your answer to moving the magnet towards the conductor, which is incorrect. Both of them are, in fact, correct, and both of them would create electromagnetic induction. So here, because C does not have the word only, we choose C as the correct answer. The diagram shows a short-circuited copper coil swinging about an axis at right angles to a strong magnetic field. The motion induces a current in the coil. Like we said, there is a coil and it's moving, it's swinging, and the magnetic field is fixed in position. But because the coil itself is moving, so the interaction between them is constantly changing. And if we have a changing magnetic field, then we have induced electricity. What is the effect, if any, of this induced current in the coil? The induced current has no effect on the movement of the coil because copper is non-magnetic. The induced current produces a magnetic field of constant magnitude in the coil. The induced current produces forces that assist the change causing it. The induced current produces forces that oppose the changes causing it. Well, the correct choice here is choice D, and this is just a principle you should understand. Anything induced has to oppose what created it. Why is that? Let's say we have phenomenon A, and phenomenon A induces or creates phenomenon B. If B amplifies A or supports A or increases A, then B will increase A more, and then A will increase B more, and then B will increase A, and then A will increase B. In terms of energy, this means that this system will keep amplifying and amplifying until it has sort of a nuclear energy effect. It has a huge amount of energy, because if they're both increasing each other, that doesn't make any sense, because the energy will keep multiplying and multiplying until it reaches a huge amount, and that doesn't make any sense. So in general, in principle, if something creates something, if A creates B, B has to reduce or oppose A. Otherwise, you would have infinite energy. And while we wish we had infinite energy, this is not something that is realistic in real life. So definitely, anything induced has to oppose the change that caused it. So the correct choice here would be choice D. A student investigates electromagnetic induction. She has a bar magnet and a coil of wire that is connected to a sensitive ammeter. Which movement does not cause a reading on the ammeter? Like we said, for there to be a reading on the ammeter, you need to have current in the wire. So you need to generate electricity. In order to generate electricity, you need to have a changing magnetic field. So moving the coil to the right, this is a change because the coil will be closer to the magnet. So the magnetic field is increasing in a sense. So there is a change here. So it will generate electricity. Moving both of them at the same speed, no, this will not generate electricity. Moving both of them towards each other at the same speed, definitely yes, because they're getting much closer together. So the magnetism is increasing. Moving the magnet to the left, again, this causes a changing magnetic field because the magnet is getting closer to the wire, so the magnetic field is increasing. So A, C, and D would generate electricity. And A, C, and D would cause the ammeter to show a reading because they generate electricity, so the ammeter will read a current. The only choice that does not cause a reading on the ammeter is choice B, because there is no changing magnetic field. Since they're moving in the same direction at the same speed, there is no change in the magnetic field. So the correct choice here is choice B. The diagram shows a bar magnet and a coil of wire. The bar magnet is moved at the same speed in each experiment. In which situation is the largest EMF induced? Like we said, EMF or current are induced due to a changing magnetic field. So the largest change in the magnetism creates the largest EMF. So in A, the coil is stationary and the magnet is moving to the right. In B, the coil is stationary and the magnet is moving to the left. In C, they are moving towards each other at the same speed. In D, they are moving in the same direction at the same speed. So in D, there is no induced EMF. The induced EMF is 0. In A and B, this change is kind of the same. One of them is getting closer, the other is going away, but the rate of change of magnetic field is kind of the same. So if we assume that here 2 volts are generated, here as well we will have 2 volts generated. However, in C, they are moving towards each other. So it's like one of them is moving with double the speed of the other. So if the magnet is moving at 5 meters per second to the right, and the coil is moving at 5 meters per second to the left, that means that the distance between them is decreasing by 10 meters per second, in a sense. So this has the greatest effect. They're getting closer to each other the fastest. So in a sense, we experience the greatest change in C, and therefore here, for example, the induced EMF would be 4 volts. So C would show the greatest EMF induced. Diagram 1 shows a magnet being pushed into a coil that is connected to a center 0 galvanometer. Which row shows the directions of the pointer when the magnet is as shown in diagrams 2 and 3? So for diagram 2, the magnet is stationary. So if the magnet is stationary, there is no electricity generated, there is no induced EMF or induced current. So the galvanometer is expected to not point anywhere. It will not record the reading. It should point towards 0. It should point up. Excuse me. The galvanometer should point up towards 0. So for diagram 2, it's either B or C. We neglect A and we neglect D because in diagram 2, the galvanometer cannot detect any current. What about diagram 3? First of all, the magnet is moving, so it's definitely not 0. So definitely this is wrong. And this tells us that C is the correct answer. Just to confirm the answer, it makes sense that the galvanometer is deflected to the right because, well, let's sort of describe this in more detail. Just FYI, we already know that the answer is C. The correct choice is C, but let's take this as an opportunity to study the idea of Lenz's law, which says that induced current opposes the change that created it, right? So in diagram 1, the magnet is moving down into the coil, right? Now, this will induce a current, this will generate electricity, but we said that the induced current must oppose the change that created it. So the magnet is moving down, so the induced current must be generated in such a way as to sort of resist the magnet. So to resist the magnet here, you want to push it up in a sense. So to push it up, you get south here and north here. So that S and S repel each other and the magnet moves up. So the magnetic field generated by the induced current in diagram 1 is such that the north pole is below and the south pole is above. What about diagram 3? Again, the moving magnet generates electricity, but the generated electricity has to oppose the change that created it. So the magnet is moving down. I want to sort of help it move up. I'm resisting its escape from the coil in a sense. I want to attract the magnet back up into the coil. So this is N. So to attract N, you need to have S here. If you have S here, you have N here, right? So if you compare diagram 1 and diagram 3 in terms of the magnetic field generated, you have S on top and N at the bottom in diagram 1, and you have the opposite poles in diagram 3. So therefore, the arrow here will deflect to the left. Then that tells us that the arrow here must deflect to the right. And this is confirmed by the answer in choice C. The galvanometer pointer deflects in the opposite direction. This is a bit more detailed. You didn't really need all of this to figure out that it's C. By elimination, we know that A is wrong, D is wrong, and definitely B is wrong as well. But it's important and it's good to understand how these things work. For paper 4, maybe. Anyway, so the correct choice here is choice C. We'll now move on to AC generators. An EMF is induced across a wire when it moves through the magnetic field between the poles of a magnet. Which electrical device operates because of this effect? Obviously, we said that magnetism creates electricity. So how do we make use of that in real life? We have what we call an AC generator, which uses this idea of a changing magnetic field to generate electricity. So C here would be the correct answer. In an AC generator, a coil is rotated in a magnetic field and an EMF is induced in the coil. In which position of the coil does the EMF have the largest value? So this is something you need to understand. The magnetic field lines are going from N to S as such. For the greatest effect, for the greatest induction, you need the coil to be cutting across the magnetic field lines perpendicularly. So when does that happen? Remember, this coil is moving in a circle like this, as they pointed out with the arrows. And the direction of motion of anything moving in a circle at a certain point is the tangent to this point. So here, at these points here, the direction of motion are tangents to the circle like this. So in A, the direction of motion is very much perpendicular to the direction of the magnetic field. The field is horizontal and the motion is vertical. A is actually the correct answer because we want the direction of motion to be perpendicular to the magnetic field. Let's just, for extra information, let's analyze the rest of the drawings. So here in B, the magnetic field lines are again horizontal. The tangent to the circle here is sort of like this and like this. So this is not perpendicular, and therefore it does create EMF, but it does not create the maximum EMF. In C, the coil itself is perpendicular to the magnetic field. So the magnetic field is horizontal, and the coil itself seems perpendicular. And some people might choose C, but this is a mistake because when the coil is perpendicular, the tangent, remember this, it's moving in a circle, right? So at this point here and at this point, the tangent to the circle is horizontal. So the direction of motion is parallel to the magnetic field. So actually in C, induced EMF is 0. This is where there is no generated electricity. At this particular point, there is no generated electricity whatsoever. At point D, or in choice D, I mean, again, this is a horizontal magnetic field and the tangents are sort of like this. So there is some induced EMF, but it's not the largest. One final comment here is that if we look at these 4 stages, A, B, C, and D, we can translate them onto a graph that looks like this. So this point here would be location C, and this point here would be location A, and B and C are somewhere here and here. So as to understand the amount of generated electricity in each position. A, of course, is the maximum. I think I made a mistake. Yeah, I'm sorry. This is D, not C. This is D. C is 0. A is maximum. B and D are intermediary values, in a sense. So for the largest value, we choose A. Which diagram represents the voltage output of a simple AC generator? This is what we just drew. B is an alternating, it sort of looks like an alternating current or alternating voltage graph. And this is the output of an AC generator, of course. So B here is the correct answer. The diagram shows how the voltage induced across a coil changes with time as the coil spins in a magnetic field. Which graph shows what happens when the coil spins more quickly? So when the coil spins more quickly, you have a greater change or greater rate of change of magnetic field. And when the coil spins more quickly, because the magnetic field is changing at a much greater rate, you get more electricity. Because like we said, generated electricity has to do with the change in the magnetic field. So as the change increases, the generated electricity increases. So first of all, we expect the graph to have higher peaks, sort of like this. Right? But this is not the final answer. Because furthermore, As the coil spins more quickly, you expect the graph to have more cycles per second. So instead of, aside from being larger, aside from having greater peaks, greater amplitudes in a sense, you also expect greater frequency. It's going to look something like this. So let's look at the choices. In B, there is basically nothing happening. In A, the amplitude increased, which is correct. In D, the frequency increased, which is correct, but not complete in either way. In C, the amplitude increased and the frequency increased. So that's what you want. You want the amplitude to increase, but you also want the frequency to increase as well. So C here would be the correct answer. A simple electric generator induces an electromotive force EMF. Which modification would increase the induced EMF? Increasing the number of turns in the coil of the generator would definitely increase the generated electricity. If you have more turns of wire, you have more interaction between the wire and the magnetic field, so you have more current in the wire. Increasing the distance between the magnetic poles is wrong because this would weaken the magnetic field, so it would weaken the generated electricity. Reduce the strength of the magnetic field, that's exactly the same as B. Reverse the direction of the magnetic field, it would not increase or decrease the EMF, it would just have the opposite direction. But the strength of the EMF itself will be the same. So again, D is wrong. So A here would be the correct answer. A wire moves in the direction shown between the poles of a magnet, which change increases the magnitude of the induced EMF across the ends of the wire. Again, moving the wire faster, of course, would be the only correct choice here. Increasing the gap is wrong because it weakens the magnetic field. Using a shorter and a thinner wire are also irrelevant here. Moving the wire faster would increase the rate of change of the magnetic field, and it would sort of increase the rate of the interaction between the wire and the magnetic field, and this would generate more electricity. Finally, we move on to something called Fleming's right-hand rule. Fleming's right-hand rule says that if I have, so bear with me here because the drawing isn't very easy. This is your thumb. And this is your maybe first finger. And this is your, I apologize for the quality of my drawing. So this is your first finger here. This is your second finger. You need to know that the second finger, due to the C here, remember it with this letter C, represents the current. And the first finger, FF, represents the field. And the thumb, I don't know why I wrote this as a P, I'm sorry, this is thumb, the B. Thumb represents the thrust or the force, basically, the direction of motion, the motion of the wire in a sense, right? Let's try to imagine how this will work together through the questions. You're using your right hand here to represent thumb for thrust, field in first finger, and current in second finger. Okay, so a wire connected to a resistor is moved in a magnetic field. Current is induced in the direction shown. In which direction is the wire moved? Now, try to use your hands to, as I'm going to dictate right now. So your second finger should be in this direction. And so this is your second finger. Your middle finger in a sense. And your first finger should be in this direction. excuse me, I made a mistake here. Sorry. Your first finger should be in the opposite direction. Why is that? So the second finger is in the direction of the current. So the current here, I'm going to draw it in green. This is the direction of the current, right? So this should be the direction of your second finger. And then your first finger should point in the direction of the field, which I'm going to draw in red. From north to south, this is the direction of the field. So this should be the direction of your first finger. If you try it with your hands, the only way that this works is if your thumb is pointing downwards. So the only way that your hand can be positioned in a way so that your first finger is to the right and your second finger is out of the page is if your thumb is pointing downwards. And if you want to imagine it better, if this is you here sitting in front of the laptop or whatever, looking in this direction at the laptop screen, your right hand is stretched to the right. Your first finger is in this direction. Your second finger is sort of pointing out of the page. So this is first finger. This is second finger. The only way your hand works is if your thumb is pointing down. So if your right hand is pointing away from the screen, so the second finger is away from the screen and the first finger is to the right, the only way your hand would maintain its shape is if the thumb is pointing downwards. So the correct choice here would be choice C. This is the direction of the motion of the wire represented by the thumb. Same idea here. Actually, it's exactly the same. The current is moving from X to Y. So again, this is your laptop screen and you're sitting here and you're extending your right hand in this direction. So this is your arm, your right arm, right? So the current is moving out of the page. So your second finger should be here. And the field is moving from north to south. Let's represent that in green. So your first finger should be in this direction as well. Just like the previous question, the only way your hand would work here is if your thumb was pointing downwards. Sorry for the lousy drawing, but if you try it with your hands, you'd find that the only way this works is if your thumb is pointing downwards. So the direction of motion of the wire is D. And this brings us to the end of our video. I hope this was useful. Thank you for watching.